Namaste everyone. Welcome to CET NEET classes. So we have seen some of the questions in electric field and potential. Now we will move on to some more questions. And we have left with I think some 31st question. Now we will go to the other one. That is potential difference, work done, converting it into energy and using electric field and finding out acceleration and all. So the things, namaste. So things involved in here are these formulas. Potential at any point is the work done in taking the charge. So that work done gives you the energy, velocity, kinetic energy, everything. So potential difference between 2 points is the work done in taking a charge, W by Q. What is the work done then? Work done by the field or work done against the field. It is Q into V. Now suppose you take a charge against the field from one point to another. Potential energy will be stored in the charge and that gets converted into kinetic energy if you leave the charge. For example, suppose you have two charged plates plus positively charged, negatively charged, and the electric field is like this. I am trying to explain the situation here. Now when you keep a positive charge here, that will be repelled and that will be attracted by this one. So as it moves, the field will do the work. Work done by the field in taking the charge from here to here is seen as kinetic energy of the charged particle. So kinetic energy will increase. By the time the charge reaches here, what is its kinetic energy? That work done itself can be equated to half mv squared. That is what you have to do. So work done can be equated to mgh, any form of energy equation depending on the situation and depending on the problem. So it can be equated to half mv square, it can be equated to mgh, it can be equated to force into displacement, anything. So this is one form of equation. Of course, here it is given, and you know the potential energy between the two charges when they are separated by a certain distance. Q1 and Q2 are the two charges separated by a small distance. Then what is the potential energy between the two charges? It is 1 by 4 pi epsilon naught, U equal to 1 by 4 pi epsilon naught, Q1, Q2 divided by the separation between them. And again you have one more formula, electric field. Suppose there is an electric field, any charge, touch charge will experience a force in that electric field, and the force that it experiences is given by EQ, F is equal to EQ. And because E is equal to F by Q, electric field definition itself says it is the force per unit charge or force per charge kept at a point. And this F equal to EQ can be equated to MA. Because EQ is F, it can be equated to MA. So if you want to know what is the acceleration of the charge, so this charge will be moving in the direction of electric field and it will be increasing its velocity every now and then because it is in the same field throughout. So field will exert a force on the charged particle again and again. So its velocity keeps on increasing. And when the velocity increases, there is an acceleration. Acceleration is given by this. So I equate F equal to EQ to MA. So acceleration is equal to EQ by M. And we use this method of finding the acceleration of the charged particles, that is free charges in a metal, electrons, and we find out the drift velocity by taking the average velocity. So this is the acceleration. And if you want to know what is the final velocity of the charged particle after traveling for a time t, you can use this acceleration and you can equate it to V is equal to V naught plus AT. And if you want to know what is the distance traveled by the particle when it moves through a certain distance, x equal to V naught t plus half AT square. So all the equations of motions will come into picture. This is how you equate or relate that our mechanical equations, mechanics equations to all these electric field phenomena, because finally they are one and the same. So if you go to the questions will be like this. So this is a brief explanation of that topic. Now the questions go like this. The first question, that is 32nd one. A charged particle Q moves around a charge plus Q along the circular path of radius r from A to B. So here the charged particle is moving from A to B, right? So it is moving from A to B. So it is moving around a charge Q. So there is a plus Q here. There should be a plus Q here. So plus q I will write. A charged particle small q moves around the charge plus q along the circular path of radius r from A to B. What is the work done? You know, work done is always equal to force into displacement, and moreover work done in a circular path is 0, because when you move around a charged particle like this plus q like this, and the force of repulsion between this test charge q and this q is always like this, and you are displacing it like this. So whatever the displacement, whether it is full circular path, half circular path, an arc of a circle, wherever you go, the force of repulsion like this and the displacement are in perpendicular direction. Work done is force into displacement into cos 90 you get, and the answer will be 0. So work done in circular path, whatever be the force, whether it is due to gravitational force, a satellite revolving around the earth, whether it is an electron revolving around the nucleus, in a circular path, centripetal force is always normal to the displacement. Work done by a centripetal force is 0. So option is 4th one. Okay. Next, 32nd over, 33rd one. Yeah. Two charges plus 5 nanocoulomb and minus 5 nanocoulomb are placed 0.1 meter apart. Work done in taking a charge of 1 nanocoulomb through a distance of 5 centimeter on the perpendicular bisector of the line joining the charges. So you have a dipole like arrangement, plus 5 nanocoulomb and minus 5 nanocoulomb are placed separated by some distance apart. Their question is, on the perpendicular bisector, what is the work done in taking the charge from one point to another? On the perpendicular bisector, all the points are at the same potential, and if it is a dipole, the potential is 0 here, because this distance and this distance will be same. This positive charge will create some plus V potential here. Same amount of minus V is created by this charge. So net potential is 0. So everywhere it is 0, because here distance from here to here same, here same. So perpendicular bisector will be separated, or all the points on the perpendicular bisector will be at equal distances from the charges of the dipole. Net potential is 0. So what is the potential difference between the 2 points? Of course, if the potential at a point is 0, don't come to the conclusion immediately that no work is done, because there may be a potential at another point, because potential difference is the work done in taking a charge, right? So work done in taking a charge is potential difference. So there may be difference, but fortunately or unfortunately, don't know, because as far as problem is concerned, it is fortunately. These points are in the same potential. Potential difference is 0. The potential is also 0. Difference is also 0. So no work is done, because delta W is equal to delta V into delta Q. Delta V itself is 0. So no work is done. Option is 0, right? First option. Okay. Again, next problem. Right. Two charges plus 2 nanocoulomb each are separated by a distance of 1 meter. The work done in bringing them 0.5 meter closer. Already they are separated by a certain distance. What is the work done? Suppose certain distance 1 meter. What is the work done in bringing them 0.5 meter closer? Already the spring is in a certain compressed position. Already it is having potential energy. Compress it still more. What is the work done? Work done is equal to the new potential energy minus old potential energy. Work done is always equal to change in energy. So what is the initial potential energy? You know the formula for potential energy, 1 by 4 pi epsilon naught Q1 Q2 by R. So what is the initial potential energy? Initial potential energy is 9 into 10 to the power 9, two charges, 2 into 2 into 10 to the power minus 18, minus 9, both are 2 nanocoulomb charges, divided by R. Distance between them, 1 meter. Okay. So what is this initial potential energy? 36 into 10 to the power minus 9 joules. 1. What about the new potential energy, U2? New potential energy U2 is equal to, again 9 into 10 to the power 9. Bring them 0.5 meter closer. New distance is 0.5. 1 minus 0.5. You are bringing 0.5 meter closer. The new distance is 1 minus 0.5. 9 into 10 to the power 9. That 2 into 2 into 10 to the power minus 18 divided by 0.5. New distance. So 0.5 is 1 by 2. and so this is 2 times greater than this, 1 by 2, this is 2, 4, 8, so 8 into 72 into 10 to the power minus 9 joules. So work done is equal to the difference in the energy U2 minus U1. U2 minus U1 is 72 minus 36. 36 into 10 to the power minus 9 joules. Here is the answer. Correct? Right? Okay, very simple question, right? But only the thing is, it becomes simple only when you know this and know the ideas. Unless you don't know the formulas and ideas of this problem, it is not simple. Calculation is simple, that's all. But idea, you must have the clear idea of the problem. Okay, shall we move on to the next one? 35th problem. On moving a charge of 20 coulombs by 2 centimeter, 2 joule of work is done. So, suppose there is an electric field, you have to push the against the electric field a charge. Suppose the electric field is like this, positive charge must be pushed in the opposite direction. On moving a charge of 20 coulombs by 2 centimeters, 2 joules of work is done. Then the potential difference. Potential difference between any 2 points is the work done in taking a charge, delta W by delta Q. But you are asked to find out, okay, what is delta W? 2 joules of work is done. Here centimeter doesn't matter, because if you want work done using distance, then force into displacement. But we are given with work done directly, 2 joules of work done in bringing 20 coulomb of charges. 2 by 20 is 1 by 10, 0.1 volt. Here is the answer. 0.1 volt, direct one. Sir, why that 2 centimeters is given? Just to mislead you, right? There is nothing to do with 2 centimeters, whether you move by 2 centimeters. And that 2 centimeters is needed if you are finding the electric field, delta V by delta L. Then for electric field, such distances are needed. Okay. 36. A mass of 1 gram carrying a charge of Q falls through a potential difference of V. This is very important question now. Not so easy to think of. Unless you have been practicing, you have a habit of practicing problems, then you can solve this. A mass of 1 gram carrying a charge Q falls through a potential difference V. What do you mean by falling through a potential difference V? Just moving in a potential difference V. Moving in an electric field is a falling in potential difference. For example, when you drop a ball, it is falling in gravity, right? Similarly, in an electric potential difference, if a charge is moving, it is falling through a potential difference V. The kinetic energy, so don't be under the impression that falling means falling from top to bottom. It is falling under gravity. Falling in an electric field means moving in an electric field. So the kinetic energy acquired by it is E. It is kinetic energy. When a mass of 2 gram carrying a charge of Q falls through a potential difference V, what will be the kinetic energy acquired by it? First of all, who are playing here? What is the team? What are the team members against which kabaddi match is going on now? It is the team members are potential difference, mass, and okay. Then what else? Potential difference, mass, kinetic energy. Which formula connects you with the potential difference, mass, and kinetic energy? Simple. Work done in taking the charge is work done per unit charge is the potential difference. So what is work done? Potential difference into charge, and that is also equal to kinetic energy of the charged particle. Am I right? It is kinetic energy. Q into V is potential energy. That gets converted into kinetic energy. Now here is it. What they are changing. Initially the potential difference is V. Am I right? Initially the potential difference is V. Kinetic energy acquired by it is E. This is what is said. Totally it is said that it is E. When a mass of 2 gram carrying a charge of Q, they have doubled the mass. Is it doubled? Yeah, 1 gram is doubled to 2 grams. Mass is doubled and falls through the same potential and of the same charge, carrying the same charge, same potential difference. If you look into the left part of the equation, same Q, same V. Will the potential energy work done change? No. But sir, mass is changed. The change in mass will produce not the change in kinetic energy, will produce a change in velocity. If you change the mass, the velocity will decrease. Suppose you want to lift a lighter stone in the same gravity, you may pull it faster. If you are given a heavier stone, you may pull it slower, so that energy spent is same in lifting it to a height h. Energy spent is same, because in the problem Q doesn't change, potential difference doesn't change. What do you mean by that? Total kinetic energy doesn't change, but they have changed mass. Because of change in mass, heavier mass may move slower, will adjust its velocity such that work done is same. There is no difference in the work done. So kinetic energy remains the same and no change in kinetic energy. Q and V are remaining the same. Option is this one. Very simple. So nothing to work out, just analyzing it. This is what is physics and mathematics involved in it, but no writing numerical mathematics, just analyzing it. So very important idea. Okay, unless you understand it, you cannot solve this problem. But here, of course, it is in one angle it is very easy. Once you understand it, it is very easy. So potential difference not changed, charge not changed. We will have such type of problems in the second stage, right? These are all direct problems now. Of course, this is not a very direct problem. We will have such problems in the second stage also. We will do some few more problems. Okay. Yeah. 37. A free pith ball. Pith ball means, pith ball is a type of spear constructed using the core part of the stem of a tree. If you remove the core of the stem of a tree, you will get a material, powder. It is made into a very light ball and it is given a charge. It is lighter. A free pith ball of mass 6 gram carrying a positive charge of so much, 1/3 into 10 to the minus 7 coulomb. The nature and magnitude of charge that should be given to the second pith ball fixed at 5 centimeter vertically below it, so that the upper pith ball is stationary. So you are given two balls. You have to give a charge. Already charge is given to the upper ball. The lower ball has to be given another charge so that they don't move. The lower ball has to maintain the upper ball by using an electrostatic force. Why does the upper ball fall? Gravity, because it is placed vertically on the ground. So very simple problem now again. So you are given a pith ball like this, which is lighter, and its mass is 6 gram. So what is its weight? Weight is mg. Mg is equal to 6 into 10 to the power minus 3 kg into 10 I will take, because I have answers, you have to select it. And what about it's a charge, and it has been given a charge of 1/3 into 10 to the power minus 7 coulomb. Okay, charge of the pith ball is 1/3 into 10 to the power minus 7 coulomb. Okay, you are given, say this is plus. For the time being, we will assume that it is plus. You are given with another pith ball. What charge must be given to another pith ball? Positive or negative? Definitely positive, because it will fall down, it has to be maintained. So that this pith ball repels this one with a force of repulsion, and it is separated by a distance of 5 centimeters. This is the problem. Analysis of problem is over. The repulsion force given by this second pith ball, of course its mass is of no importance. Say that it is kept on a table, so we are not worried about its mass. It should repel this one with such a force that it should balance the weight of this, correct? So it is simply like some Millikan's oil drop experiment, isn't it? Little bit of similar fashion, but in Millikan's oil drop experiment we maintain an electric field in the upper direction so that it maintains the weight of the ball. Weight of the oil drop, sorry, right? So shall we equate these two? Mg must be equal to F, electrostatic force of repulsion. What is Mg must be equal to 1/4 pi epsilon naught Q1 Q2 by R square. That implies, I can use this part of the board now. You can see that M 6 gram into 10 to the power minus 3 into 10, 6 gram into 10, 9 into 10 to the power 9, this one, Q1, Q2, 1Q is given, 1/3 into 10 to the power minus 7, correct? In another Q is not given, Q2 divided by distance square, 5 centimeters square. They are separated by a distance of 5 centimeters. 25 into 10 to the power minus 4. Because it is 5 centimeters square. Now cancel as much as you can. 3 times. 3 2 times. However, Q2 is here. I have to bring this here. So that implies 50, right? That is the only number. Of course, all the answers are 5s. Otherwise, I could have selected it now only. Suppose only one answer is 5. Suppose the other answers were 600, 1000, 550 and something like that. I could have. And minus you can delete, because if this is given minus, that will be attracted. So because it is vertically above, suppose this is here and this is here, this should be given minus, so that to attract it against gravity. But now it is vertically below, it is given, right? The other charge is kept vertically below, so this should be given plus and this should be given plus. So plus is the answer, either 500 or 50. Okay, so what is this? 50, 25 into 250. Then what else? Here minus 7 and here minus 7. Gone. This minus 7, this one and this one I will club. Minus 7 and this minus 7 gone. 10 to the power minus 9 when it comes here. 15 to 10 to the power minus 9 and plus fourth option. Okay. That is the correct answer. Very good. And once you understand the idea, very easy problem. Correct? Okay. We'll move on. Yes. Yeah. 38. Similar type of problem. A metal sphere having a charge of 2 into 10 to the power minus 4 coulomb is placed directly below at a separation of 0.1 meter from the bob of a simple pendulum, okay, of mass 54 gram at rest. The charge that should be given to the bob so that the tension in the thread becomes 0. That means thread should be free. That means the charge kept below should manage the other charge, right? So here is a pendulum, say plus, it is at rest, it is not oscillating. Here is another charged body. The charge that must be given to the lower body, right, should be given to the bob. Okay, what is Q on the bob? So that the tension in the thread becomes 0. That means the mg part of the tension should be cancelled by the electrostatic force. Electrostatic force must be cancelled by mg. And what is this distance given at 0.1 meter from the bob? Yes, below, and at a separation of 0.1 meter from the bob, and simple pendulum mass is 54 gram. So this is 54 gram. Okay. Shall we have the same method? Yes. F electrostatic must be equal to mg. Now I will directly write F electrostatics. 9 into 10 to the power 9, 1 by 4 pi epsilon naught. Q1, Q2. 1 is given the charge. Yes, this is a metal sphere is given the charge. 2 into is already charged. Q1, Q2, this one, divided by distance square, 0.1 whole square, 10 to the power minus 2. 0.1 is 10 to the power minus 1, whole square, 10 to the power minus 2, equal to, what else? Yeah, mg. M is 54 gram and G10 I'll take. This is 6 times. Do you have different? We have different answers now. We are very blessed with the different answers. 6 and what about 2 coming here? 3. This is the only answer possible, right? That is the only answer, because these 2 3s are. Now what about minus 9? Will we get that? In the examination you need not check, because you will save the time. 10 to the power 9, 5, and when it comes to the denominator, minus 7, minus 7, minus 10, minus 9. You get it. You can check it and you can see that. Correct answer. So, and here, one more thing I want to say. We are going to discuss it later. You have another type of arrangement here. What type of arrangement, sir? You can have it like this. Suppose you have a pendulum. How to proceed I will explain. I have not included that type of problem. I am planning to discuss it in the second set. Now suppose you have a pendulum like this. Suppose it is given plus Q. And if it is kept between the plates of a capacitor, plus, charged positively, charged negatively, and if there is an electric field like this, uniform electric field, what will happen to this pendulum? definitely this pendulum will be displaced, because this positive charge will experience a force in the electric field and it will try to move in the direction of electric field. Now, suppose some missing term in the problem, either mass of the bulb or strength of the electric field or tension in the thread, some question. But how to proceed? Now this thread is stationary, that pendulum is balanced. It is balanced under the action of three forces. In the first year PU you have studied long back, you may be remembering. So mg, weight, and this is electrostatic force. Can I write it as EQ if E is given, electric field is given, F is equal to EQ, this is Q, right? And this is the tension in the thread. Now split this into components. Split this into components. I will draw a normal. You can see that it's also green in color. This is theta. Okay. Now split this into components. How do you split this into components? Tensions in the string. You know this method, right? This is T cos theta. And again, component of T here, T sin theta. If this is stationary, T sin theta should take care of EQ, the pulling force horizontally like this. And if this is stationary, T cos theta must take care of mg, T cos theta must take care of mg, and T sin theta must manage EQ. Okay, so divide it, tan theta must be equal to mg by EQ. Any one term may be missing in this problem, find it out. That's all, very simple. So you can do that. Find either angle at which it bends. If this is theta, this is also theta, right? Right. That's how we can do that. So that's just an extension of this problem. Okay, we will move on. Move on to the next one, 39. Yeah, torque. You know the formula torque. Whenever a charged particle or a dipole especially is placed in an electric field, it experiences a torque, and torque is given by, suppose an electric field is like this, then the charged particle will be arranging itself like this. Say this is dipole, and the dipole axis will be like this. Positive charge will be bent to this side and negative charge here. Suppose the dipole is kept like this. Now it experiences a torque. This is the stable equilibrium position. Here it doesn't experience a torque. Here it experiences a torque. One force like this, another force like this. Net force is zero if it is a uniform electric field. But there is a net torque. And suppose the dipole moment is like this, and angle at which the electric field and dipole moment are oriented is theta, then torque is equal to Pe sin theta, or it is the cross product of P and E, P cross E. It is a vector quantity. So P sin theta. Now, what is the work done in turning it from here to here? Work done is minus Pe cos theta. Right? So it is P cos theta. So these two formula, P dot E. So energy, potential energy stored is P dot E, work done is minus P cos theta. Okay, with this information, I don't spend much time for whatever you have studied in the theory, because it's a waste of time. If you have not followed this, go to your theory notes and turn it and see that. Okay, most of you will be knowing this, no problem. Okay, now, work done to deflect a dipole by an angle of 180 degree from the stable equilibrium position is given by, this is a stable equilibrium position. If the electric field is like this, dipole oriented like this, minus the force like this, force. These forces are not separated by a distance. There is no arm for the couple. So now the torque is zero. From here, this position, you have to bring it to 180 degrees. So you have to turn it and put it in the 180 degree. Now plus will be repelled like this and minus like this. So here is plus, here is minus. If you want to turn it by 180 degree, what is the work done? Right? Work done to deflect a dipole by an angle of 180 degree, it is given by W is equal to Pe cos theta 1 initial position minus cos theta 2. So what is the energy in the initial position? Pe cos theta 1. What is the energy in the final position? Pe cos theta 2. Take the difference. W is equal to Pe cos 0 minus cos 180. Cos 180 is minus 1. Okay, cos 180. Okay. This is W is equal to Pe cos 0 is 1 minus of minus 1. Right? Difference in the energies of the two positions. It is 2 PE, third option. So work done in rotating through 180 degree from the stable equilibrium position, cos 0 1, cos 180 minus 1. So 1 minus of minus 1 is 2 PE, PE cos theta. Okay, that is the formula. Right, the next problem, last one. Yes, an electric dipole of dipole length 2 cm is placed with this axis making an angle of 30 degree with a uniform electric field of 10 to the power 5 Newton per Coulomb. Okay, if the torque of the dipole is so much, then the potential energy is, right? Potential energy stored in a dipole is, you know that it is P cos theta. Okay, let us not worry about the negative and positive signs. What about the torque acting on the dipole? It is given uniformly. Torque acting, the electric dipole of length 2 cm is placed with this axis making an angle of 30 degree with a uniform electric field. Torque you can find out. Torque tau is equal to, just you are asked to find out if the torque of the dipole is so much, its potential energies. Torque is P sin theta. So only difference is cos theta and sin theta. Torque is 10 root 3. P don't know, E don't know. Same PE here, right? So that's why I am using the torque formula. P sin theta, sin 30, half. Right? Angle, see, check the angle, which angle is given? Angle between the electric field and the dipole moment. Is it so? The axis is dipole axis is making an angle of 30 degree, correct? With the electric field, that's correct. If some other angle is given, so even in many problems, you must be very careful while writing the angles, whether the required angle is given or the other angle is given. So otherwise sometimes you may need to have 60 degree as the angle if 30 degree is given, because if the other angle is given. Okay, now it is same angle, sin 30 half. So what is P? P is 20 root 3, right? P is 20 root 3. Put this 20 root 3 here. You get potential energy U is equal to P 20 root 3 cos 30 root 3 by 2. This is root 3 by 2. Same angle. So this is 2 gets cancelled with this one. 10 into 3, 30 joules. Finished. So it is 30 joules. Okay. So this is a set of problem. 10 questions. That's all. I want to check whether I can upload this to YouTube or not. That's why I am stopping at this moment, and we will come along with, we will speed up a little bit once we are very familiar with how to communicate, because I don't know how to upload this video. If I put it in some app, there will be lagging, voice lag and all. So once this is, once we are set with all those types of technical problems, we will move faster. Okay, so work out these problems. You have the PDF with you, and see those answers again, whether they are correct or not. Can you remember it once again? That is very important, because if you can't remember it, if you understand it now, if you can't remember it in the exam, everything is gone. So you have to keep the memory till the examination, at least till the day of examination. You have to keep the memory even after that, but that is very difficult task. So you have to unload some of the things, unwanted things again and again, otherwise the memory will be full. So till then, till the next class, work out the problems, extra problems also. Keep cheering and be happy. Get prepared for the entrance examination. Thank you for watching. Thank you.